we are ready, I think, for this evening's talk by Professor Somnath Dasgupta. Professor Somnath Dasgupta is a geologist. He did his PhD from the Jadavpur University. Afterwards, he joined the Geological Survey of India for a few years. Then he joined Jadavpur University as a faculty. He shifted to Indian Institute of Science Education and Research, Kolkata in 2009. In 2014, he took over as the 5th Vice Chancellor of Assam University, Suture. So with prudent academics, he has mixed administration as well. He's back to Kolkata with jointly at ISI, Indian Statistical Institute, Kolkata, as well as at ISAR, Kolkata. He is a recipient of several national and international awards, including the J.C. Bose Fellowship from the Department of Science and Technology, Government of India. Professor Somnath Dasgupta will tell us about physical diversity. Professor Dasgupta.
Thank you very much for this invite, and a very challenging job to present in front of young children about physical diversity in India. So the topic of today's discussion is physical diversity in India, and this particular subject actually transcends the boundary between physical geography and geology. I am basically a geologist by profession, so I will dwell on geology a little bit more, but physical geography tells us about the physical diversity in any place in the world. And in this particular context, we are talking about India. So physical geography tells us about the divisions, physical divisions of India. But this is a subject which people, young children, have read quite a lot in their geography textbooks in school. And so therefore, I will not go into great details of that. So I'm holding this slide for one reason. That is, at the bottom of the slide is my email ID, which is somnath@isarcol.ac.in. So if the young audience today, if you have any question which comes into your mind later in the day, in the evening, or tomorrow, or any time in future, you may please write to me, and I will be very happy to answer your queries. So how shall we proceed today? We will discuss a little bit about the physiographic details of India, because we have to establish that we are diverse in physical meaning. I will not talk in much details about that. As I said, that in your school geography textbooks, you have learned quite a lot. So I will just summarize the physical diversity from a geography point of view. And then I will try to address a major issue, that whether there is any correlation between physiography and geology. Because as you know, geology is a subject which deals with the science of the earth, and it deals with how the earth formed, why the earth formed, how it evolved, how it helps to sustain humanity, and how it helps to sustain the environment or climate. Now, we have to know about the correlation between physiography and geology a little bit, and we'll see that there are broad correlations, but there are mismatches as well. Then I will go into some details of the processes that operate deep in the earth, but which control surface features, because we are talking about physical features. So we need to know the processes which form those physical features. And finally, I will deal with the question how, why, and when some of the surface features developed in India. I emphasize the word some because I cannot within this limited time, cover everything. So that is the limitation. Nevertheless, I will talk about what I consider to be the most important surface features. I will talk about their origin and how, when, and why they formed. So, even on this scale of a map of the world, if you look at India, you will see several colors. And these colors tell us about the diversity. Each color represents a particular physical feature. For example, this light green color tells us about the plain lands. This dark brown colors, these are hill ranges or mountains. And these are the high tablelands that occur in the central part of India. So even on this scale, which is a very small scale, the whole world is in front of you. Even in this scale, we have three colors in India. So it shows that physically we are diverse. But the details will come out much more in the next slides when we enlarge the Indian portion. So this is what you have learned in your school textbooks about the physiographic divisions of India. We have the Himalayas on the north, the mountain ranges. We have this green region, which is plain land, a huge plain land called as the Indo-Gangetic alluvium. And then this particular color is a high plateau, which we call the Central Highlands, followed by downwards is the Peninsular Plateau. This brown color is the Peninsular Plateau, which in some textbooks is called Deccan Plateau. And then we have these different colors along the coastlines of India, which are the coastal plains. This is the eastern coastal plain, and these are the western coastal plains. And of course, we have beautiful beaches, as you all know, all along these coasts. So that's the very gross picture of the physiographic divisions of India. And in addition, we have two sets of islands in Bay of Bengal, the Andaman Nicobar Islands here, and in the Lakshwadhi Island in the Arabian Sea. So we have everything in India, from mountains to plain lands, to coastal regions, to high plateau regions, to islands, everything. So it is truly diverse physiographically. Going into a little more details, in the Himalaya, in the what we call the peninsular India, excluding the Himalayan range, we have the hill ranges like the Aravalli Hill Range in the western part, the Western Ghats in the western coastline, the Eastern Ghats along the eastern coastline, and so on. These are the hill ranges. We have the Vindhyan hill ranges here, or the popularly known as Vindhyas, and the Satpuras. For some strange reason, I don't know exactly why, the area north of Vindhya is called northern India, and the southern part is called southern India. It's just a geographical nomenclature. It has got no other meaning. We have the Thar Desert on the western part of India here, and we'll talk about the Thar Desert a little bit in more details. We have a very interesting physiographic feature here in the western part is the Run of Kutch. And we will again talk about the Run of Kutch in a little bit more details, because our final goal is to show you how these diverse physical features formed. This is the Thar Desert in the western part of India. A small part falls in Pakistan. but 80% of the Thar Desert is in India, covering the states of Rajasthan and a little part of Gujarat. Now I come to the geological map of India. Now, there are several colors. As you know that we have different geological formations. These dark colored patches, what we see here, are comprised of very old rocks. Their age is from 3,300 to 500 million years old. It's quite a big range. Nevertheless, these are the old portions. Now, just as a baseline, let me remind you that the Earth is 4,600 million years old. So we are seeing, when we see a rock of 3,300 million years, we are seeing quite an early stage rock in the Earth's history. And then we have these huge yellow portions, which formed much recent times, about 1.6 billion years. Now, 1.6 and 3,300, you can immediately imagine the diversity in age. And then we have other rock formations like this green one. This is the famous Deccan Trap. This green one formed at 65 million years ago. And interestingly, this time coincides with the extinction of dinosaurs from the world. So there are lots of hypotheses about any possible correlation between Deccan volcanism, or the formation of the Deccan plateau, or the Deccan traps, as we call in geology, with the dinosaur extinction or not. Now, this is, of course, there are a lot of hypotheses, and we are not going to discuss at length, perhaps some other time. But this is one of the hypotheses. But there are many more. And then you have this pink color material, which are of something like 1,000 million years to 200 million years old. Then we have these rocks, which are about 65 to 5 million years old. So you see that in terms of geologic age, we have also diversity in India. Our rock formations start from 3,300 or even 3,500 years, and we have very young rocks forming even today, where, please remember, barren islands in the Andaman Nicobar group, where lava has come up very recently and formed new rocks, new igneous rocks there. So we have a tremendous diversity in geological age, and of course, all these different colors represent different kinds of rocks and soils or material. So there is no uniformity anywhere. You can see the range of this is 3,300 to 500 million years. So naturally, the rock types are also diverse. So we are living in a paradise of diversity, in the sense that we have the real possibility to explore the diversities in the physical world if we live in India. So now comes the key question, that do we have any correlation between these two maps? On the left side, you have the physiographic division, and on the right side, you have the geological divisions. You may be able to see that there are some correlations, in the sense that this huge portion of the Deccan, or the southern or the peninsular plateau region, is actually composed of these very old rocks, which we say 3,300 to 500 million years old. But the similarity also exists here. The yellow portion corresponds to the green portion here, almost in toto. So we have very young sediments which formed here. I already said less than 1.6 million years ago. And this is reflected in this physiographically in the Great Plains of Indo-Gangetic alluvium. So there are certain similarities, but if we look at this particular inflection in the map of India, which is the Gulf of Cambay, and proceed to the east, we'll see that we enter the green area, which is the Deccan Trap. And if we move north, from this, we are in the Deccan Traps. But physiographically, for some reasons here, the Deccan Trap is part of the Central Highlands as well as a part of the peninsular plateau. So you see there is no match between the physiography and the geology. Deccan Traps cover these areas. So it is transcending the boundaries between two plateau regions as described by the geographers. So they don't match really. And also you will see that these hill ranges, which are the Aravalli hill ranges, these are also coming under this Central Highlands, as well as the Vindhya ranges. It does not discriminate between the hill ranges and the high plateau regions. So the physiographic division is just for description, so to say, but if you want to have a genetic meaning, then you have to look at the geology of the rocks and the materials and find out how they form. Now, one fundamental issue here is that the Earth's surface, therefore, comprises of different materials of different ages, but the surface interacts with the atmosphere, the hydrosphere, and the biosphere. And the surface suffers weathering and erosion, and also affected by movements of the surface due to internal processes. We already know these days plate tectonics is taught in the school, so you know that how plate tectonics operate, although I will talk about plate tectonics a bit. But you need to understand that the Earth's surface is getting constantly changed. Of course, these changes do not occur in our lifetime because we were talking in terms of millions of years, not in human lifetime. So unless some catastrophe happens, these changes are really gradual. It takes millions of years to happen. So we will never feel it unless, of course, there is a catastrophe. So the factors which control the surface features of the Earth, or as we call it, the Earth's topography, are the tectonic processes. That is fundamentally plate tectonics, which causes uplift of the regions. The most common example being the Himalayas, which all of you know. And this uplift suffers a competition from climatic processes which control weathering, that is physical and chemical disintegration of rocks, then erosion, that is the transportation of this weathered material by wind, water, and glacier, and then finally deposition of this eroded material somewhere in deep basins. And one needs to emphasize that the Earth's surface is continuously reshaped due to this competition between uplift and denudation. and leading to peniplanation, that finally everything should be peniplaned because of weathering and erosion. But as I said, we'll not see it in our lifetime. It takes millions of years to do that. As you can see, that the rock which has formed 3,000 million years ago at great depth in the earth, maybe 30, 40 kilometers, we can quantitatively say that, and then it is sitting right on the top of the Earth's surface. So it means that it has come up to the Earth's surface because the top was removed. The top was removed by the processes of weathering and erosion. That's how the Earth's surface changes with time. So we have to look into the deeper portions of the Earth to understand how the tectonic processes operate and how they change the Earth's surface. So we all know that the Earth has got three broad layers, which are both chemically distinct and physically distinct. These are core, mantle, crust from the inside. And the core has got two portions, which is the inner core, which is solid, and the outer core, which is liquid. There is a strong difference in chemistry between the material constituting the Earth's core, the Earth's mantle, and the Earth's crust. So there is a difference in both physical properties and chemical compositions between these layers. The upper part of the Earth's mantle is quite rigid and couples with the crustal portions to form what is known as a lithosphere. This is the lithosphere, which is, and below that we have a very highly viscous mantle which convects. This, perhaps you have read that this is the driving force of plate tectonics. The outer layer of the Earth is therefore the lithosphere, which constitutes totally the crust, which can be a continental crust or an oceanic crust, and the upper part of the mantle, which is quite rigid. So this is the thickness of the plates of plate tectonics. So the plates are not very thin. They are about 100 kilometers to 150 kilometers in thickness. And these plates are in continuous movement with respect to each other in the Earth. So that is what we know as plate tectonics. And this is the plate boundaries that we have today, along with the velocity of movement of these plates. The maximum velocity of the plate that we have recorded is here in the Nazca plate off the coast of South America, which is 18.3 centimeter per year. So this is absolutely measurable quantity. So these are the plate boundaries, and we have different names for these plates, but let us concentrate on our India. So India is a part of the Indo-Indian Australian plate, which includes the Indian Ocean, Sri Lanka here, and this is the boundary between the Eurasian plate and the Indo-Australian plate. And this boundary is our Himalaya. So Himalaya is located at the boundary between the Eurasian plate and the Indian plate. Now there are also some subplates. This Indo-Australian plate is the full plate, but it has got some other subplates inside. Let us look at these arrows. Some of the arrows are diverging. They're moving from each other, and some of the arrows are converging. You can see they are converging. The arrows are towards each other. So we have different kinds of plate boundaries. Some are divergent plate boundaries, like this one. you see they are moving in opposite directions, or convergent plate boundaries like this one moving towards each other. In North America, we have another kind of plate boundary where the plates are sliding past one another. You can see they're parallelly moving, but in opposite directions. So we broadly have three kinds of plate boundaries. The plates are in constant motion, as you can see from the figures, the velocity centimeter per year. They're moving continuously with respect to each other. But the total area of the Earth does not increase. So it means that plates are being created as well as they are being destroyed. We will look at those things now. So that is what I was telling, that there are three main types of boundaries: divergent boundaries, where the plates move away from each other. And a good example is the ocean floor mountain ridges, which are known as Mid-Atlantic Ridge or East Pacific Rise or Indian Ocean Ridge, you must have read. And then we have plate boundaries which converge to each other. For example, India converged onto Asia to form the Himalayas in between. That's a kind of convergent plate boundary. And we have a third plate boundary I was talking about, North America, that is the transform plate boundaries, where the plates are sliding past each other. There's a lot of earthquakes everywhere. There are a lot of earthquakes because of these plate movements. Perhaps you have watched the film San Andreas. That's based on the movement on the San Andreas Fault. So the first kind of plate boundary is the continent-continent convergence, where two continents collide. The Indian subcontinent collided with Asia to produce the Himalayan mountain chain. This is one kind of convergence. Another kind of, and these are the areas we have maximum earthquakes. Now, you can almost draw the boundary of the plates from the location of these earthquakes. You can see that most of the earthquakes in India or in the neighborhood, they occurred along the plate boundary. So you can almost draw the plate boundary by plotting the location of the earthquakes. Tremendous number of earthquakes, and compare with the internal part of India. There are very few earthquakes inside India because these are very stable regions. So they are very tectonically stable. So they do not suffer a lot of earthquakes, but they do suffer. We have the 2001 Bhuj earthquake, for example. Now it caused a lot of damage, and these earthquakes are mainly along deep fractures within the Indian plate. This is not a plate boundary. This is within the plate we have fractures. And those fractures get activated due to earthquake which originated somewhere else. But the earthquake waves arrive here and then they displace rock bodies along the fractures. So they are cause some kind of earthquakes. But most of the earthquakes are in the Himalayan regions, as you can see. Just to complete the picture, we can have another type of convergent plate boundaries where oceans converge on continents. And this we don't get in India, but the question is, it is very famous on the western coast of South America, where Mount Andes formed because of this particular convergent plate boundaries. There is another, this is the transform plate boundaries that I discussed, that the plates are moving parallel to each other in opposite directions. And the good example is the San Andreas Fault in California. These are some examples of divergent plate boundaries. I will not talk much because this talk is not on plate tectonics, but I will just point out one thing, that these are the oceanic ridges, which are the divergent plate boundaries. And these are in the oceanic plates, but this can happen also on the continents. That is what I want to point out, that it can happen along deep fractures within the continents. For example, the Arabian plate and the African plate was one time together, formed a single plate, and they were divided by the formation of the Red Sea in between, that because the two plates got separated from each other. There is a divergent plate boundary. And this particular thing is continuing today also in the southern part. So this is a very important observation, that continents can break. We already learned that continents can join, because India collided with Asia to form the Eurasia, India, Eurasia, a same continent. You can walk across the Himalayas to Europe. But here what you see is a continent can break as well. And this is the standard diagram for plate tectonics. As we said, that this is the lithosphere, which is moving, and we have convection in the Earth's mantle, which is dragging the lithosphere. So the driving force of plate tectonics is this motion, convective motion in the Earth's mantle. And where the mid-ocean regions are located, where the rising limb of the convection current, and these are the oceanic trenches, which are where these are the downgoing limb of the convection current. And an example of the oceanic trench, you know, the Mariana Trench off the coast of Philippines is the deepest point on the Earth's surface, and there the plates are going down. So plates are created here, they are destroyed here, as a result of which the Earth's total surface remains constant. We came to the major conclusion that along convergent boundaries, continent can join, and along divergent boundaries, continents can break. So when they join, we call them as supercontinents. So because different continents come together to form supercontinents, and then the supercontinents break, just like the Africa broke, and then we have along that the continents then start moving in different directions as the part of the plates. And this particular cycle of formation of supercontinents and their destruction is known as Supercontinent Cycle. And in the Earth's history, we had many over the last 3 billion years. Perhaps you are most familiar with the last one, which was called Pangaea. But before that, we had other supercontinents like Gondwana, East Gondwana, Rodinia, and so on. India was all along a part of the upper trajectory: Colombia, Nena, Rodinia, East Gondwana, Gondwana to Pangaea. India followed this particular trajectory. Others followed the other trajectories. So this is the history of the continents in the last 3 billion years. That's a very general depiction of the history. So we had supercontinents, and we had the supercontinents break up, and they form, then they again join over a period of time. And we do the correlations very easily, because if two continental blocks were together at a particular time, this should have same geological history at that time. So by deciphering the geological history with a time connotation, I can easily find out whether the continental blocks were together at a particular time. So these are some of the pictures of the supercontinents, the predicted configuration of the supercontinent of Colombia. You see India was located on this side, very close to North China. So please try to focus on India. I am pointing because otherwise it becomes very complicated if you look at the entire picture. So India was very close to North China and East Antarctica. And we are still close to North China, actually. Then came the supercontinent of Rodinia. Here you can see India is sitting here, North China is sitting on the opposite side. So a lot of movement between North China and India. India was still close to Antarctica during the formation of Rodinia, which formed around 1,300 to 900 million years and broke up. That is, the supercontinents also break. So they broke up around 700 million years to form Gondwana. And here you can see the Indian shape, which is lying very close to Madagascar and Australia and East Antarctica. So India and East Antarctica had a very close relationship all through, as you can see. But the others changed their position. But they were very close altogether. And then this is the 300 million years old supercontinent of Pangaea. And again, you see India here, very close to Antarctica, Australia, and Africa. So we were all neighbors here, and this entire mass was one continental block, which Alfred Wegener, who first postulated continental drift, he drew this configuration. It is more or less confirmed by later studies. Then came the sad story of India divorcing Antarctica. And as you can see, 90 million years ago, India moved quite apart from Antarctica. In between, the Indian Ocean formed. And this is the trajectory of India, approximately 5,000 kilometers in 140 million years. India traveled from Antarctica northeastwards and then collided with the Eurasian plate on the north to form the Himalayan mountain chain. And the ocean, which was lying in between India and the Asian continent previously, is known as the Tethys Ocean, which is no longer there. As you can see, you don't see any ocean between India and Tibet, for example. So this Tethys Ocean was completely lost, and India moved northeastwards and collided with the Eurasian continent here, and the Himalayas formed somewhere here on the north, in between. Given this background that how India evolved, then we also have to look at the divisions of India from the geological map that I presented. There are some portions of India which are called Cratons. There are different names. Don't try to remember the names, but it is important to see the buff-colored areas. These are Cratons. These are very stable regions. The city of Bengaluru is somewhere here. Kolkata is somewhere here. And there are 5 different Cratons which formed before 2,500 million years. And these regions were formed later. These are called fold belts. These are actually the stitching material which stitched the Cratons together. And so we have the entire shape of India formed like this. So the Cratons are actually the nucleus of the continents. These were the nuclei. And then they were joined by these fold belts to form the entire continent. So you can say that these Cratons are the nuclei of the continents to form. This greenish portion is the Deccan Trap, which is about 65 million years old. Nothing to compare with 2,500 plus million year old rocks of these buff colored areas. So this is 65, and these are more than 2,500, often 3,300 million years old. So I will quickly go through that how India evolved through geologic time. This was how India looked like at around 2,500 million years. You can see the physiographic map. So at that point of time, we had mostly these portions. These are these portions. So we had these portions and some here of this. I don't know what was the distance between these two. What was in between, we don't know, actually. That happened around 2,500 million years. Then around 1,600 million years, India was trying to take its shape. You see some of these fold belts formed in between, and they stitched the Cratons. So they were coming together. The Cratons were coming together. India was taking a shape. Around 900 million years ago, a large portion of India became in existence because the fold belts, they joined the Cratons, and you can see an outline forming around 900 million years ago. There were a lot of white portions in the map. This is the portion which is now occupied by the Deccan Trap. The Deccan Trap formed 65 million years ago, and we are looking now at 900. So this area is empty now at 900 million years ago. The Indo-Gangetic alluvium, which is much younger, is also white 900 million years ago. Then we come to around 500 million years ago. You see the southern portion of India now joins the other part of India here. So India is almost complete other than these portions. And now at the present day, we have the gap here is filled up by the Deccan Trap at 65 million years. And these white portions are the Indo-Gangetic alluvia. So this is how Indian map developed over a geologic period of time. These are, of course, cartoon diagrams, so not very accurate, but nevertheless, that gives you a general picture of the development of the map. And this is the physiographic map, once again, located on the right side. So you can see that how this physiographic map was constituted in a geological sense over a period of time. So this is again the physiographic map. Now I am going to the last stage of the talk, in which we will talk about that how, why, when some of the surface features developed. So as a starting point, I again show you the physiographic map, and we start our journey from the plateau regions. These are the plateau regions. This was the peninsular plateau or the Deccan Plateau, and this was the northern plains or the northern plateau, and this was the Chotanagpur Plateau. Now you can compare with the geological map. You will see there is a similarity here, because this part of the Deccan Plateau actually matches with part of the Dharwar Craton and part of the Deccan Trap. So remember, Dharwar Craton is 3,300 million years old and Deccan Trap is 65 million years old. But they are physiographically very similar, as you can see. Then the northern plateau is actually these Cratons. These Cratons are the northern parts of and this Chotanagpur Plateau is actually this Craton. So there is a similarity, broad similarity, in the sense that the high plateau regions of India are by and large the Cratonic blocks geologically, that is the very stable part of the Indian continent and constituting of very old rocks. The Indo-Gangetic Plain or the northern plains, as you know, that this is divided into physiographically the Punjab plains, the Ganga plains, and the Brahmaputra plains. Now, the story of the plain is something that related to the rising of the Himalayas. So because of the rising of the Himalayas, a basin formed at the bottom of the rising Himalayas. And that particular basin was filled up with sediments, and these sediments came from both the rising mountain chain of the Himalayas and also from the high plateau region of the Indian continent. Then, about 1.6 million years ago, these basins were separated into two parts, and the southern portion was filled up with a large part of the sediments, while the northern part then became a part of the Himalayas, the famous Shivalik range, and rose at higher altitudes. So the lower part, the basin, then became filled up with sediments, produced what is today known as the Indo-Gangetic Plains. It is 150 to 500 kilometer wide, 300,000 kilometers square in area, and very important, it is the bread basket of India. So supplies most of our rice, wheat from this particular thing. These are the alluvium plains formed by the rivers, mainly the river of the 5 rivers of Punjab, coming from Himalaya, rise from Indus, Ravi, Chenab, Bias, Sutlej, and then the Ganges and the Yamuna in the central portion, and Brahmaputra on the east. So that is why the entire northern part of India is covered by thick alluvium of the major rivers. These are called the northern plains or the Indo-Gangetic Plains. This formed around 1.6 million years ago. Now, coming to the other very interesting physical feature of India, this is the Thar Desert. And I will tell you that we can have some dating done on the sands as well, forming in the Thar Desert or anywhere. We dug deep sections through the sand dunes and measured their ages, and also studied the pollens that were buried deep inside, and even some plant fossil kind of thing. And you can understand from the pollens and the fossils what was the climate at that time. So you have the age and you have the indications about the climate. It shows a very interesting pattern that up to 10,000 years, the area had a semi-arid to wet climate. It changed dramatically at around 10,000 years, and then it became very wet first. You have a lot of plant fossils and lot of pollens preserved in the depth of the sands, which shows that it was an area flushed by rivers and it was very wet. And then it started to become very, very dry. And the present level of aridity was reached around 4,000 years before present. Around 4,000 years, the present level of aridity. Although there are quite a large amount of population still staying in the Thar Desert, but the interesting point is the next slide. When we look at the Harappan civilization sites, and please remember your history books, that is the pre-Harappan is 6,500 BC, and then the Harappan civilization, different stages of the Harappan civilization. And we have discovered many important sites of Harappan civilization. Rakhigadi in Haryana is a pre-Harappan site. 6,500 BC. And then this part is falling in Pakistan, of course, Mohenjo-daro and Harappa in general, these are falling in Pakistan, but we can see very nicely preserved sites of Harappan civilization here at Dholavira, Lothal, and lot of places. Now, these are the areas which are now part of the Thar Desert. So how can a huge civilization flourish in a desert climate? Impossible, because you need rivers, you need transportation of material. And so this particular anomaly was solved by looking at satellite imageries when we observed that under the sand there are huge old channels of rivers. Now, I will not talk about much on this topic because here lies a huge confusion, because this is a confluence of religion, mythology, and science. And it is very difficult to segregate one from the another. So I will not talk much about it, but the question is, regarding the science, in particular archaeology, we know that there were huge civilizations here. And we also know that these are covered by the Run of Kutch or by the Thar Desert, which are not habitable at all. So it shows that there were immense river systems flowing through these areas 4,000 years ago. And most of the researchers believe that the present day Ghaggar-Hakra river channel was the site of the mysterious Saraswati River. Now, this is a mysterious river which has been referred in Rig Veda, Mahabharata, and Ramayana. But the question is, where is the location of Saraswati? That is a speculation. Whether this was Saraswati or not, we don't know, because this is, as I said, is a complete mix-up of religion, mythology, and science. But nevertheless, it is true there were river systems here. And this is what the map looks like. Today is the river stops here. These blue lines are the today's river. The Indus is flowing in this direction. And here we have a small river called Luni. It is just a monsoon river. It has water only in the monsoon time, otherwise completely dry. And this is the entire portion is the Thar Desert. So, and this is the site where we get the evidence of Harappan civilizations. So people think that this Ghaggar-Hakra channel, this was a major river channel, dashed lines here, and then came the mythical Saraswati, that people say that this was the Saraswati River, which has been referred in Rig Veda, Mahabharata, Ramayana, etc. I don't know whether this was Saraswati or not, but as a scientist, I can tell you that this was a river, no doubt about it. And there were huge civilizations around this. So you see that what I said, that the Thar Desert is a very recent formation, 4,000 years ago, that is clearly shown by the sites of Harappan civilization. It cannot be a desert climate which can support such civilization. Impossible. Then we look at another diverse feature in India, the famous Run of Kutch, which is unparalleled in the world. And one should visit these places. It's a huge salt pan. The thing is, it's on the western part of India, the Run of Kutch here. And you see, this is a huge salt pan. It's seawater evaporated and produced these salt crystals. And there are some people, nomadic tribes, they stay there. There are a few villages here and there, but by and large, not inhabited at all. The climate is harsh, and this particular place is, we are very lucky to have such a unique feature in our country. And this is also part of it is shared by Pakistan as well. Now, geology tells us a very interesting thing about the run of Kutch. It formed very recently. During 1819, there was a major earthquake in the Kutch area, which raised the ground by 5 meters on one side. And it became, average is about 4 meters, 12 feet. And see, 10 feet, 80 kilometers of area rising by 10 feet. So now you can understand that how much force is required to raise a portion. And because of this raising of the portion, it created differential elevation. River channels were blocked. So during the wet season, the seawater came into the run, and in the dry season, this seawater got stagnated, and then it got evaporated, produced those salt pans. So basically, the present day run of Kutch is only 200 years of age. It's nothing as compared to the geological ages we were talking about. So this particular one is known as Allahabad. That is an elevated ground of the god. And this is a close-up picture of that elevation. This was caused by a major earthquake in 1819. So it is, we know exactly the date and everything because these were properly recorded. And then the area became accessible for the sea water only during the wet season. And then this water got dried and evaporated, and then you form the salt pan. So today's run of Kutch is very young in age. Then we look at the islands, the Andaman Nicobar Islands. This is a part of the Indo-Eurasian plate boundaries. And this is at the boundary of, there is a subplate which is called the Myanmar plate. And this one is this is the same collision, the Andaman Nicobar Islands formed during the same collision which produced the Himalayan mountain chains. And Andaman Nicobar Island is actually the southward extension of the Arakan-Yoma mountain range. And part of it is covered under the Bay of Bengal, so you cannot see. But if we send sound waves, we can see the shape of the mountain submerged in the Bay of Bengal. On the west coast of India, we have the Lakshwadhi Island, which is a completely different kind of island. It is made up of corals. It's a coral island. The corals, they made the houses on volcanic rocks, igneous volcanic rocks, and they formed big reefs. And they finally rose above the sea level and then seawater and formed the island. So Lakshadweep is basically a coral island. So even within the islands, we have diverse. Andaman Nicobar is not coral island, although tourists go and see some corals there, but it is not a coral island. Lakshadweep was totally a coral island. So from the island point of view also, it is quite different. Now, finally, we come to the mighty Himalayas. Of course, the Himalayas, 2,500 kilometers long, formed due to Indo-Eurasian plate collision, but it is also not a monotonous mountain range. It has got several divisions, which are both physiographic as well as geologic. From the south, you have the Shivalik ranges, then we have what we call lesser Himalayas, then higher Himalayas, and this is the Tethyan sedimentary sequence and so on. Mount Everest is located here in the Tethyan sedimentary sequence. Now, this is interesting because near the top of the Mount Everest, we have rocks, limestones, which formed on the sea floor. That is on the sea floor of the Tethys Ocean, which is no longer there. It is completely consumed by the Indo-Eurasian plate convergence. Now, if the limestones formed on the ocean floor, on the sea level, or the below that, and now they are sitting about 9 kilometers above elevation. So this tells us very clearly that the ocean floor has actually been elevated by 9 kilometers. So that's what I was saying, that plate tectonics can cause this upliftment, and erosion and weathering, they reduce the elevation. This is a competition going on. The boundary between the Indian and Eurasian plate is here in the northern part. It's called the Indus Sunport Suture zone. Suture is, you can understand, it is the stitching zone, and Sangpo is the name of the river Brahmaputra in China. So this is the Indus Sangpo Suture zone, and we have the Nanga Parbat sitting here, K2, the second highest peak, sitting here, and then you have the Tibetan plateau beyond the Himalayas. So look at how the Himalayas formed. The Indian plate came, the Tethys was here, and the entire thing got under the Eurasian plate. So this left side is the Indian plate, right side is the Eurasian plate. This is the mountain range, that's the Himalayas. And beyond that, you have the Tibetan plateau, the high plateau. So within the mountain range, you have several divisions, like I said, Shivalik range, Lesser Himalaya, Higher Himalaya, and so on. And each area within the mountain range has got different physiographic expressions as well. That is what I will show you in the last slide, that each of these areas has got different physiographic expressions. And a trained eye can distinguish whether you are in the Shivalik Himalaya or in the Lesser Himalaya or in the Higher Himalaya. The reason of this difference is because these are composed of different material subjected to different types of tectonic forces, and so that is why they are quite distinct. And this is how the Lesser Himalaya look like, the standard thickly vegetated portions here and not much of high elevations. You move to the higher Himalayas, you see the snow-covered mountains, and you see deep incision of forming the deep valleys. Often the top to bottom difference is more than 10,000 feet or 3,000 meters. This is the higher Himalayas. So you can see the difference also visually from here to here. If you go to the higher plateau, then you find this peculiar thing. That is, it's almost like a plain land. Only thing, it is located at an altitude of 5,000 meters or high. So it is very cold. It is a plateau region, but very unlike the plateaus in the peninsular India, these are very high plateaus. So you have the Tibetan plateau, and if you move farther north, of course, you encounter the roof of the world, the Pamirs, which is even higher and even more plateau kind of features. Here you can see some hills here, but basically this is plain land. And on the western part of India, we have a cold desert. We talked about Thar desert. It is an arid, warm desert. And in Ladakh, you have a cold, arid desert. Hardly any rainfall in Ladakh, hardly. And you have hardly any vegetation. You have some small rivers flowing, kind of nalas flowing, and you have miles after miles of this landscape of barren hills and barren lands. This is called the cold desert. So within the Himalayas, we have a lot of diversities in the physiography. And this, I hope that I have brought out the main features of diverse topography or diverse physical features, and hope that I have explained at least some formation of some of them. You know, Himalayas formed at the collision between India and Asia took place at 50 million years, and Himalayas started forming at 23 million years before now. 23 million years before now. And then let us so explore some unity, as Professor Mojumdar was saying. Let us explore some unity amidst all these diversities. I always end my talks with this beautiful photograph of the Guru Tomar Lake in northern Sikkim near the Indo-China border. It's a glacial lake located at around an altitude of 6,000 meters. If you have not gone there, please visit. This is what I call a heaven, the heaven on the earth. Thanks to the Academy Trust, the National Council of Science Museums, and the Indian Academy of Sciences for giving me this opportunity. You may read a rather simple textbook, Making of India by Professor K.S. Valdia, published by Springer in 2010. Thank you very much.
Thank you, Professor Dasgupta, for the very informative talk. I was wondering, well, you have explained that the methodology to some extent, namely satellite images, and then you said you dug deep into probably the sand dunes of the third desert. But I was wondering if you could enlighten us about how one knows. I mean, it was like a story to hear about the tectonic shift and see these pictures where India was close to Antarctica, then moved away, etc. How are these things known?
Actually, that's what I said, that the best way to do it is to compare the geology of the areas which were supposedly adjacent. So we know the rocks, we see the rocks, we see that when they formed, how they formed, at what time they formed. This is very important. If we have on two sides of the continent separated by a big ocean, the same rock type, same time formed, and then as if they were just separated and the ocean formed in between. And the important constituent is to know precisely the age of formation. And of course, after life came into existence, we can correlate with fossils. That's a much more convenient way to demonstrate, because fossils, you know that if you have land fossils of the same age in two different continents separated by 5,000 kilometers of ocean, then obviously the two lands were together at that time. That is why only they had the same thing. Otherwise, one is sitting in a temperate climate, another in the pole. So how can the same fossil be present there? Same kind of life, or plant or animal. How can it be? Unless they were together at a convenient place. So that is one thing. And another issue is paleomagnetism. That is the orientation of the magnetic minerals in the rocks with respect to the Earth's magnetic pole. So if you know the time of formation of the rock, and if you can measure the paleo poles, you know where that particular rock was at that particular time. And matching paleomagnetic poles, we can easily find out such correlations. Because you know that the Earth's pole changed its orientation.
So there's a question from one of these viewers, that what technologies are used in identifying these features that Cratons have come together, as you explained. So how these geological features came together, what technologies are used?
Actually, you start from the field work, that is our starting point. We see, collect samples and do then study them with our naked eye. Then we make sections to study under optical microscopes, even scanning electron microscopes. Then we can determine micro compositions of the constituents of the rocks. Then we use some physical and chemical principles like thermodynamics and kinetics to calculate the conditions of formations of these rocks. And then we can know, and we use radioactive decay equations to calculate the ages. So altogether, these kinds of technologies are used. So we use a lot of instruments, analytical instruments of different kinds.
Basically, I think because these are students would have been they would be interested in knowing future career prospects. So whether technologies or what fields to pursue, I guess, is what the
actually, most of my talk was centered on solid Earth. But Earth science as such is a system science. It encompasses ocean sciences, atmospheric sciences as well. Quite a lot of atmosphere sciences, ocean sciences. So, and lot of biological sciences as well, when you particularly look at the fossils and other things. So you see, it's strictly a very multidisciplinary unit subject to study. And you can develop, depending on your choice, you can develop in different directions. Like if you are interested in physics, you can develop into a geophysicist, looking at earthquakes, looking at exploration for oil and other gas and other stuff, etc., etc. If you love chemistry, you can become a geochemist and look at the things that I was taking, the application of thermodynamics, kinetics, and other features to rocks and atmosphere. You can study the aerosols. You can study the climate change. In the ocean sciences, you can study the tsunamis, etc., etc. There are a lot of opportunities and a lot of government and private departments who employ earth scientists. Of course, the universities and research institutions are there. So we have quite a lot of art departments are teaching earth sciences. As you know, that Indian Academy of Science started recently, relatively recently, compared to that, I think 2009 or 10. And of course, West Bengal has the culture of earth science teaching right from the beginning. Presidency College came both in Madras and Kolkata. They started teaching earth sciences quite early. And of course, in the Statistical Institute, we have a geological studies unit as well. And if you are interested in biology, you can go into the paleobiologic aspects. You can do a lot of paleobiologic stuff on how the dinosaurs, the story about the dinosaurs, story about different kinds of life forms, etc., etc. And there are opportunities both in the academic career, research career, as well as professional earth scientists and geologists, because you see the Mausam Bhavan, you can work in the weather prediction, you can work on the climate change, you can work on many avenues. So I work on solid earth, so I was emphasizing solid earth science.
It's very interesting. I've been to the some of the Himalayan ranges. I do a lot of trekking. So I've visited with lots of students, other interested people. I've taken my own daughter to some of these. I haven't gone to this Guru Dongmar lake, but I have been to many such high altitude lakes. And as you said, it's very startling to see, green bugyals up on top of those Himalayan mountains.
Right.
They look like as if they're on the Gangetic Plain, but you see those beautiful places up there.
Beautiful. I mean, there were river channels and other things, and you can see they're very peculiar. For example, if you have a deep valley and there's a small river flowing, climb up the hill, you will find river deposits at on altitude of 3,000 meters. Now, how can the river deposit be taken there? It was not done by human beings. So the river was flowing there. It has cut the valley. So you can see the amount of erosion that the rivers can do. And we see that what we try when we try to play tricks with the nature. You saw what happened in Uttarakhand.
Mm-hmm.
Try to block the rivers and you see the effect. So that is the problem, but we have to live with that. We need power and we need good roads, and I understand. But safety is of paramount importance.
Not only that,
Professor Dasgupta, I have a question.
Yeah.
How can we very accurately date very ancient rocks? Because we know that carbon dating and all has a period that beyond that.
Yeah. Carbon dating.
So in that case, how can we predict that this is
actually carbon dating is for only 5,000 years old material. But if you want to date older rocks, you have to use the uranium-laid decay system mainly. Uranium-laid, neodymium samarium, or rubidium strontium. These are the three decay schemes which operate on half-lives of billions of years. So you can easily use them to date old rocks. So we normally use uranium-laid, samarium neodymium, and rubidium strontium. These three systems of radioactive decay, not carbon. Carbon is only for 5,000 years.
And from your narrative, it was so engrossing. I had another curiosity that when the Tethys was lifted so much by 9 kilometers, and so one may probably expect that undersea animal fossils will be available at the top of the mountain.
Yes,
is there any such definitive
it is there.
documentation?
It is there. From the Everest base camp, they found fossils at an altitude of 6 kilometers. Everest base camp. Of course, it is very difficult to study those limestones occurring at the face of Mount Everest, because you spend most of your time how to climb, not to look at the rock. And so at the base camp level, people stayed there, so they do some field work, and they have collected fossils. So it is the ocean floor which is sitting at that level. So it tells us very clearly, you don't have to speculate. This is absolutely that it has risen 6 kilometers. And actually we have limestones nearly at the top of the Mount Everest. And that limestone is a limestone which was formed in the ocean basin, in the oceanic sediment, and which is sitting at 9 kilometers high. So that's a straightforward proof.
You have been doing this for, as we could understand that you have been doing this for decades. So even I have been going to the Himalayas, and this is of great concern that we see every 5-6 years when we go back. I used to go to the Himalayas almost every year, but now because of the pandemic, I haven't. But since the late 80s and all that, you notice how much the glaciers have shrunk from.
Yes, yeah, that is a huge headache, because this glacier water is the main source of water for our rivers, and without our rivers we'll die. So the question is that why they are shrinking. The main reason here is possibly the climate change people are talking, but this is pollution level, the rise in temperature a little bit. A fraction of a degree Celsius can melt a glacier. And that is happening. So the glaciers are retreating. But the good point is that at some other places, glaciers are advancing also. So it's not that everywhere it is retreating. So maybe there is some melting at some places where we can see, and other places there are new depositions of snow. So it is a balance which we are maintaining, but you are right, on an average, the shrinkage is more than growth, and which is a huge concern, because I know that I have done, where I did my field work in 1980, I was camping on a glacier in which is called the Zemu Glacier in eastern Himalaya. And now when I went after 30 years, that I was camping on hard rocks.
Yes, yes.
So it's absolutely, I know that there's no glacier there. So retreat is a fact.
So this
We are
advancement
talking
of glacier is in Himalayas, or is it in Alps or Rockies?
No, Himalaya is the house of glaciers, actually. That is why we call it a third pole, actually. This is the world's third pole. It's the North Pole, South Pole, and the Himalayan pole. It's the storehouse of glaciers.
So this advancement of glaciers actually has happened in the Himalayas.
Advancement, no. Advancement is very little, mostly retreat.
Now, you said some advancement has happened. I was trying to understand where that happened.
Some places people reported advances in glaciers also.
In Himalaya.
In Himalaya. But as I said, 80% is on the negative side. Yeah. So the concern about retreating glacier is very much true.
On YouTube, we have people students thanking you for. One of them says that, thanks for the enlightening talk. I didn't know that run of Kutch was such a recent phenomenon.
Yeah.
So even that was a revelation even for me. I didn't know run of Kutch was just. Yeah.
Also, I didn't know that Thar Desert is only 4,000 years old.
Thar Desert, actually the entire Harappan civilization, thrived in areas which is now Thar Desert. So it is not possible to have such a civilization in a desert climate.
True.
So actually, do you place the Harappan civilization before the formation of this third desert?
Yes, actually that area might have in the name Thar, but it was not a desert at that time. It was, I don't know what is the old name of that, but the question is that it was drained by a lot of rivers at that time. And there came the story or the mythological Saraswati. Saraswati River. This is there is a lot of controversy regarding that, whether we should call it a Saraswati, because we also know that in our mythology there is a Saraswati which meets the Ganges and the Yamuna at Prayag, which flows underground. That is in our mythology. So which one is Saraswati, I don't know. But I have read many papers by scientists where this is quoted Rig Veda and Mahabharata, where Saraswati is referred quite often. So but the question is, as it happens in our country, always these things are mixed up with every mythology, religion, science all together. So now it becomes very difficult to take out. So I did not go into much details because this will raise questions that I cannot answer.
But probably the way you suggest that the post-Harappan migration might have been triggered by this change of climate as well.
Yes, that is what people, the scientists actually, they say that is because of the weakening monsoon, which was responsible for the drying up of the area. It was drained by the southwest monsoon. The weakening of the monsoon was responsible around 4,000 years ago, when gradually this became dry and dry and dry. And then, of course, once it became very dry, then this wind-blown sand, they accumulated and formed the desert. But these are very easily dated. If you dig through the dunes, then you can collect the sand particles from the bottom of the pit and determine the age when they experienced sunlight, because there are cosmogenic nuclides like beryllium-10, which is captured from the sun, solar. So now that they are buried, they cannot have any beryllium-10. So the last capture of the beryllium-10 can be dated by AMS methods. It's available in India as well. And then you can date those sand grains when they experience sunlight. That is, they were on the surface. So there are various techniques, but for geologic age, we use mostly the radioactive decay schemes.
I think that's wonderful. One who has listened to your presentation will have a very good idea and overview of the whole Indian physiography, and they can relate and place it over history very nicely.
Yeah, I hope so.
Thank you so much, Professor Dasgupta.
Thank you.